Okay, welcome to Lab 3 of Global Logistics Management. In this lab, we're going to do two mini cases on logistics optimization. And logistics optimization is trying to solve transportation problems, facility decision problems, logistics network design problems in order to reduce or minimize total cost or maximize profit. So the first case we're going to discuss today is about Papr, the paper manufacturer. And the supply chain of Papr currently looks something like this, where you have two manufacturing plants. They don't have a central warehouse, so the green layer is missing. And these manufacturing plants ship product directly to 9 regional warehouses, which are paper rolls, paper towel rolls. And then these regional warehouses in turn supply the product to the customers. They deliver to retail stores. If there is online ordering, they ship it or deliver to the customer's facility as well. So we are interested in this part of the supply chain, from plants to regional warehouses. And management wants to consider opening one or more central warehouses. Initially, we're just going to try to see what happens if you open one. If you do open central warehouses shown in green, then the manufacturing plants would be shipping to central warehouses, who would in turn be shipping to the regional warehouses. We have 5 potential sites for these central warehouses called CW1 to CW5. And we can use one or more of these sites depending on whatever minimizes our costs. And so we're going to optimize this setup to figure out what's the lowest cost setup, how many central warehouses do I need, if any at all, because if they don't minimize cost, then we can have 0 central warehouses, I guess. So we're thinking of having one or more, so we're going to find the total cost, the minimum total cost of having one or more central warehouses, and kind of compare it to the current costs we have right now, and then we can make that decision. So Papr is a paper goods manufacturer. They make products like paper towels. They make them in 2 plants in the US. From the plants, the paper towels are currently being sent to 9 regional warehouses, from where they're shipped to customers across the US. The distribution manager wants to see if opening a central warehouse will be useful, because they're having issues with keeping a lot of inventory at the manufacturing plant. So they're saying, why not we have a warehouse, a dedicated warehouse to hold the inventory, which will refill or replenish the regional warehouses. And then obviously, if you're going to set up a warehouse, it may make sense to put it in a central location rather than in the manufacturing plant itself. So potential locations for a central warehouse are 1 to 5. These locations have been identified, and this data has already been collected. Now in real life, you'll have to go out and collect this data, but for this case, we've already been given this data. So for example, if you want to ship something from plant 1 to central warehouse location 1, if you set it up at that location, it'll cost you $77 per pallet to make that shipment, okay, to ship 1 pallet. And similarly, 48 to central warehouse location 2. You can see that the central warehouse location 2 is closer to the plant 1 than central warehouse location 1, because it's cheaper to ship there, right? It's usually cheaper to ship smaller distances. Yeah. So these costs will give us the inbound cost to the central warehouse, how much it costs to bring stuff into the central warehouse. And then from the central warehouses, we can ship it out to regional warehouses. And this table provides those costs. So to ship 1 pallet from central warehouse 1 to regional warehouse 1 will cost $89. Okay. And you can see, obviously, as the locations are different, the distances are different, the costs change, right? So here, for example, central warehouse 4 to regional warehouse 3 is only $55 to ship a pallet. Okay. Now, when you open up a central warehouse, it's going to cost you something. So each pallet that's processed by a central warehouse, it has to be received, put away into storage. When it's time to deliver it, it may have to be loaded onto a truck. So you have labor involved, you have equipment involved. So all of that adds to a variable cost of $8 per pallet for warehouse 1 if we open a warehouse here, $2 per pallet for warehouse 2, and so on. You can see that in some places, in some options for the central warehouse, the variable cost is much higher, but the fixed cost is much lower. So potentially at this place, we are considering opening a warehouse that maybe has their high wage rates. Maybe this is, a state where there's the wages of workers are high, so the variable cost is high. Or maybe, this is an option for a warehouse where we're saying, okay, for each warehouse, these costs also depend on how much automation you do. The more automation you do, it can drive down your variable cost, okay? But sometimes automation requires more space for those type of racks because they're not very, the storage is not very dense. For a certain area of the warehouse, you can store less pallets if you have it fully automated, for example. So you may end up having a bigger warehouse and hence a bigger fixed cost. Or you may also have to pay financing expense and maintenance and hire, technicians to maintain that equipment, and that will also increase your fixed cost. So we see this trade-off. Some of the warehouses we can open are going to have high fixed cost but low variable cost. Some of the warehouses we can open, potentially open, have high variable cost but lower fixed cost. Our plants also, probably they were open at different times. This might be our original plant we started off with, a small plant when we were starting our business. It has high variable cost because it's probably older equipment, not very automated. And then maybe we opened a larger second plant when our business took off. And that has a lower variable cost, a higher capacity. And the lower variable cost is could be because of newer machines, better automation, things like that. Okay. Now, you might wonder, what about the fixed costs of running these plants? Well, we are not considering closing down any plant, so the fixed costs are not relevant to this problem because whatever we decide, both plants will be operating and we'll be incurring the fixed cost of both plants. However, we could decide to use different amounts of each plant, and so the variable cost is important because, we want to obviously use plant 1 first. But if you look at plant 1, it's really far from CW5, for example. Ship costs a lot to ship here. So depending on how the transportation costs affect the decision, it depends on how much of each plant we use. Okay. The weekly demand at the regional warehouses is given in pallets. So regional warehouse 1, we have to provide it 140 pallets each week. Warehouse 2, it will 180 pallets each week. And then, the warehouse will break bulk, will unpack the pallet and ship out the paper products to our customers. Okay, so that is the setup of the problem. Then a second question asks us about service level. And if you remember, logistics strategy is not just about cost minimization. We also have to think about logistics customer service. And a key part of that is the lead time for replenishment. If you provide quick replenishment, that is considered a higher level of logistics customer service, right? So in the second question, management wants us to see if we can fulfill 70% of our demand at the regional warehouses on the same day. So if regional warehouse 1 runs out of stock, and if they call us in the morning, we want to be able to replenish them by evening of the same day. And that can happen if we are within 200 miles of that regional warehouse from our central warehouse. So this matrix basically tells us which central warehouses are within 200 miles of which regional warehouses. For example, the one here shows us that central warehouse 1 is within 200 miles of regional warehouse 3. so it can replenish regional warehouse 3 on the same day, less than 24-hour lead time for replenishment. But it's not going to be able to do that for regional warehouse 1 and 2 because they're further away. Okay. You could make this matrix yourself if you were given distances. If this was a matrix of distances, you could look at where the distances were less than 200 miles and make this matrix yourself. But in this case, the question just provides us with that. So we're going to start with question 1. Just model the problem, find the optimal setup, and then we'll talk about the service level issue about, okay, can we replenish the regional warehouses? 70% of the demand can be replenished in the same day, in same day delivery. Okay. So let's go to Excel, and I have provided you with an Excel data file with all these tables already in Excel. So that'll be a starting point, and we'll build our model step by step. Now I want you to read this analysis section. Maybe I'll go over it quickly. Of our thinking about how to solve this problem. So if you look at this supply chain or logistics network diagram, we have 5 paths linking plant 1 to 5 potential central warehouses. So we have to monitor how much product flows along them. Why? Because that's how we'll keep track of transportation costs from plant 1 to any potential central warehouse. Then again, we have these arrows going from plant 2 to central warehouses. So you have 2 plants and 5 potential central warehouses. You should have 10 arrows. So 5 here, 5 here. And that will give you 10 decision variables which keep track of how much product flows along these arcs. In these sorts of logistics network transportation problem, any potential arc or path on which product can flow, you need to have a variable to keep track of how much product flows on that arc or that path. Now, looking at the next stage of the supply chain, from central warehouse to regional warehouse, we have 5 potential central warehouses and 9 regional warehouses. So from each central warehouse, we have 9 lines going out to each of the regional warehouses. So 9 plus 9 plus 9 plus 9 plus 9, or 9 times 5 gives you 45 lines. So you need to have 45 decision variables here. Then because we have fixed cost for the central warehouses, we also have to keep track of whether a central warehouse is going to be used or not. Because if you're not using a central warehouse, we don't want to count its fixed cost. And we also don't want to use any paths from that central warehouse in or out because that warehouse is not open. So we'll have a flag variable or a binary variable for each of the 5 central warehouses. So 5 binary variables. It will be 0 if we don't use the warehouse, or 1 if we do use the warehouse. So those will be the variables we need in our model to keep track of all the costs and where stuff is going from, which warehouse is open. And then we'll have some constraints. So we want to make sure that central warehouse, that plants cannot ship out more than their capacity, because let's see if we are given the capacity here, and so these plants can at most ship out a quantity which is equal to or less than their capacity. So the sum of the product flowing on the 5 paths going out of plant 1 must be less than equal to the capacity of plant 1. Similarly, you have a capacity constraint for plant 2. On the central warehouse side, a warehouse can only ship out stuff it has. So if 100 units flow into this central warehouse 1, only 100 units can flow out. That's called flow balance constraint. When you have a site with inbound shipments and outbound shipments, over the long run, outbound shipments cannot exceed inbound shipments because you can't magically create stuff. Stuff has to be received to be shipped out. And so you have a flow constraint where it says the inbound quantity sets a limit on the outbound quantity. Okay. And then we'll have demand constraints. Each regional warehouse must receive product equal to its demand. Demand is given here, weekly demand. So, for example, regional warehouse 1, the total amount it receives from any path, the total of that and you add up should be at least 140. Okay, so let's go to Excel and set it up. Okay, so this is the data file with data from the paper case. Okay, and I'm gonna start building the model in a separate worksheet so that I don't mess up any original data, and I'll copy paste data as I need. Okay, so first up, we need to handle, I'm just gonna go left right for our supply chain. We're gonna start at plants, move on to central warehouse, then go to regional warehouses. So let's look at the manufacturing plants to the central warehouse part. Okay, so here I need some decision variables in terms of what product is shipped from what plant. Okay, so this would be plant 1 shipment and plant 2 shipments. Okay, just gonna format this to get the box away. Let's zoom in. Okay, let me actually do shipments SHPM. Okay, so these will be my decision variables here. So I'm gonna color them orange. And so each of these cells will contain how much product is being shipped from this plant to this central warehouse and so forth. Okay. Now, if I add up this total, that's all of what plant 1 ships. So I can do sum of these cells. And I can see if I ship 1 and 1 and 1 and 1 and 1, I ship 5 total, right? So that's working. That's total shipped, right? And this, I'm going to use quotes, because if you don't use quotes, you put less than equal to, it becomes like a formula and it gives you an error. So this has to be, the total shipped from plant 1 has to be less than the plant 1 capacity, which is also given here. Okay. So I'll just do copy this and say this has to be less than equal to this cell, 1500. And then plant 2 shipments, again we can sum them up. And decision variables means that the solver will decide the values of these orange cells. You can type in anything you want, but it's going to overwrite them, and that has to be less than equal to equals 500. Okay. Now I can also sum what central warehouse 1 receives here, okay, to see, because central warehouse 1 can only receive shipments from plant 1 or plant 2. So whatever the sum of this row is, that is what is received by central warehouse 1. And so I'm going to need that as I build my model. So right now, if plant 1 ships 1, let's say plant 2 ships another 1, central warehouse 1 receives 2 units, right, 2 pallets. And then there's no limit on this, but we have to make sure whatever central warehouse 1 receives, it can ship out that much. So that's like the first stage of our supply chain. Okay. Now, here, I would also like to add the data of processing, because remember, when each central warehouse receives a pallet, they have a variable cost to process it. So I want to find these costs and put them in there as well. So what I'm going to do is maybe insert some columns and copy this variable cost and fixed costs for these plants right here. Okay. And what I also want to add here is going to be whether a central warehouse is open or not. All right, let's take out these borders. These are going to be my binary variables. Okay. Okay. So these binary variables will tell me whether a central warehouse is open or not, right? And if it is open, we'll factor in the variable cost, the fixed cost, and if it's not open, we'll not count the fixed cost. Okay. That's the first stage of my supply chain. So if you look at the diagram, you have plants that ship to central warehouses. So that's being modeled right here. Total quantity shipped has to be less than the capacity of the plants. And then what is the total shipment received? And then we have variable costs here, fixed costs here. These are transportation costs. So this is, I'm going to call it TRC, transportation costs. Okay. Now let's do the second stage of our supply chain. That's going to be based on these transportation costs. So we can copy them. Here. Ooh, that's very close. Let's insert a column. And you'll understand why I copied them twice. Let me just, because I can delete all of this and make this my decision variable. So each cell will capture how much product is shipped from central warehouse 1 to regional warehouse 1, central warehouse 1 to regional warehouse 2. So between the second stage, central warehouse to regional warehouses, what sort of shipments are happening are captured in these cells. If I put 1 here, that means 1 pallet is being shipped from central warehouse 1 to regional warehouse 1. And we have to make sure that if central warehouse 1 receives 2 pallets, it cannot ship out like 3 here, right? This cannot be 3 because you only received 2, so it has to be less than or equal to 2. Okay. Now it might actually help to put this table up because I need to calculate the sum of the rows here. So I'm going to insert some rows to put that big table up there. Okay, let's select this. Oops, sorry about that. Need to insert a row. Okay, select this, Control X, cut, move it up here. Okay, so that way I can multiply each of these cells by this to get the cost. Okay, now everything that's shipped out of central warehouse 1 is gonna be the sum of this row because it can only ship out to these 9 regional warehouses. So all outbound shipments from central warehouse 1, they're gonna be summed here. So we can say outbound from central warehouse, and this is inbound to central warehouse. That's coming in, the total amount. This is the total amount going out. Okay. And then I can also sum what's arriving at the regional warehouse. So anything that comes to warehouse 1 has to come to one of the central warehouses. If I sum them, this is what's arriving at each regional warehouse. And obviously, what's arriving at each regional warehouse has to be bigger than equal to the demand. So I can copy. Remember that these quotation marks and these signs are just labels. They don't tell Solver that this number has to be less than this number. We're going to do that in the Solver window. But this is just for visually for me to see, oh, okay, this is shipping out of plant 1. This must be less than this, so I can visually see what's happening. So if I look at my demand, I can copy paste this data here. and that's my demand, right? So what's arriving at reasonableness 1 must satisfy this demand. Right now it's not, obviously, right? 2 is less than 140, but solver will take care of that when I tell solver all of these things. Right now I'm just setting up these sums and setting up my decision variables, okay? Then we have to figure out, once the decision variables are set up, we have to figure out our objective, calculate the total cost, and then we can put in our constraints in solver and actually solve the model. Okay. Let me see if I can put this. Let me just put it here. Okay, so I'm going to put variable cost here and here, just because this table is to the side and I can just see right here variable cost at the plant. Is this and this. So anything that gets shipped out will be multiplied by the variable cost to get the cost at the plant. Okay, so now we're going to do our cost calculations. Okay, so we're going to have the first stage transportation cost, which is inbound to CW transportation cost. So let's call this transportation cost. So the inbound to CW is going to be these quantities right here, right? That's the inbound. So if we do some product, okay, of these cells with these numbers here. So 77 multiplies the 1, the 48 multiplies this one, and then all those terms are added up. That's what some product does. Okay, and that's going to give us the cost, the transportation cost, which is inbound to the central warehouse. And then to that, we can add plus the transportation cost of the next part, another sum product. And we select all of these decision variables and we multiply them with all of these costs for these paths, and we add it to our transportation costs. So for shipping, these 5-6 pallets and these 2 pallets, we are incurring $549 of transportation costs. When solver changes these values, this cost will go up. Then we have operating cost for plant. Okay. And the operating cost for the plants are going to be the variable cost, these sums, the total quantities shipped from these plants by times the variable cost. And that's it. There's no fixed cost for the plant. So that is just going to be some product of, or it's just 2 numbers. We can just do it individually to show you what some product actually does. So we're going to do this times this plus this times this. If I did some product of these 2 cells with these 2 cells, that it'll multiply the first cells in each array, and then plus the multiplication term of the second 2 cells. So it's 5 times 8 plus 1 times 13 for now, and then as 5 and 1 change, these costs will change. That's the operating cost for the plant, right? And to that, we can add the operating costs for the central warehouse. So operating cost for central warehouse, that's going to be the fixed cost times the binary variable, because if this is 1, 0, 0, 0, 0, then that means we only opening the first central warehouse, and we should only be adding the first cost. So when you multiply, do some product of this with this, the zeros will cancel out the fixed cost you don't need. And then to that, we will add the total amount received at each central warehouse times the variable cost. So we'll do some product, okay, of this binary variables telling us whether a central warehouse is open or not times their fixed costs, okay, and then plus do another sum product for the variable cost, all of this variable quantities that they receive times the variable processing cost for each piece that they receive. So that's the, and you can see operating cost is very high because you have the fixed cost of 100,000, right? Okay, so we added the transportation cost of both stages of the supply chain. We've had the operating costs for plants and the central warehouse. And that is it. Then we can find our total cost. That's just going to be the sum of these three numbers. Okay, so I'm going to make it bold and highlight it as yellow to remind myself that that is the cell that I'm trying to minimize, right? So we want to minimize this total cost. And our total cost is made up of transportation cost and then operating cost for the plant and operating cost for the central warehouses. So we could have more than one eventually. So we want to put S here. Okay. Okay, now we want to set up our constraints. So we have these constraints we have to satisfy demand. That's one. So let's list our constraints, right? So our constraints, okay, we have 1, demand satisfied at regional warehouses. 2, capacity constraint of plants. So the total amount shipped has to be less than or equal to the capacity of the plants. Okay, 3, we have to make sure that we do not ship anything from a central warehouse if it is not being used, if it's a 0. So if this is a 0, so central warehouse 2 is not being used, right? This binary variable is a 0, then all of these should be zeros, right? I can't put like 5 here because central warehouse 2 cannot ship out 5 if it's not open, okay? So to do that, we say the total outbound from a central warehouse, okay, this has to be less than or equal to some sort of capacity, okay? And that capacity will be 0 if this is 0 here, okay? So we will say, let's find the total demand for all the regional warehouses. So we don't have a capacity constraints on the central warehouses. The case says, you can open warehouse for any capacity, pretty much. That is going to be reasonable for our case, right? And so we can have a capacity that one central warehouse can handle all of this flow, can handle 1835 pallets or more. Right now our total demand is this, so I'm just going to set the capacity equal to the total demand, okay? And then this has to be less than or equal to that, okay? Now the capacity when it's open is 1835, but when the central warehouse is closed, the capacity is going to be 0. So I need to multiply this capacity by the binary variable. And actually I should, and I should lock, put $signs around this cell, because if I drag the formula down, I don't want this blue cell to move down because my total demand is in cell B28, right? So here's my capacity, and notice I can drag this down to sum for different central warehouses, and you'll notice their capacity is 0. But if I turn them on here, the capacity goes up. But if I turn them off here, the capacity goes to 0. So this is great. Whether we turn on and off a central warehouse, that'll adjust the capacity, which will force these rows to be 0 if the capacity is 0. Okay. And now we also want to specify a linking constraint to make sure that this number, okay, stays less than equal to what's received here in inbound. Okay, so what's incoming to the central warehouse, outbound cannot be more than that. So we need to put in a constraint to do that, and then we'll be all set to run Solver. So sometimes it's called a flow balance constraint, because what's inflowing into a warehouse, the outflow has to match that. We also, so what we're going to do here is, let me move this table up to make space. Okay. What we're going to do here is we're going to say that this inflow must match this outflow. This inflow to the central warehouse must match this outflow from the central warehouse. Okay, so now here we're going to be a little bit careful, because we're going to call it flow balance, and we're going to say okay, the flow balance is that the outflow must be less than equal to inflow. So this cell must be less than equal to that cell. Okay. Now let me show you what we have to do here. So our constraint was going to be that outflow from a warehouse has to be less than equal to inflow, because the warehouse can't create product out of thin air, right? However, a constraint like this can cause problems on a Mac, because if you have variables on, this is called the left-hand side of the constraint, and this is called the right-hand side. On Windows, it's not a problem. The solver that comes with Excel for Windows is smart. You can just put in this constraint, outflow less than equal to inflow, and it works. But on Macs, the solver is an older version, which gives a problem if this cell is calculated based on decision variables. DVs, decision variables. So what we can do, we can just use basic algebra to say, well, I can bring it here and subtract it. So I can say outflow minus inflow must be less than equal to 0. And this is identical to this. Okay, and I hope you can see that saying outflow is less than equal to inflow is the same thing as saying outflow minus inflow must be less than equal to 0. It's just basic algebra, right? And so this would work on Mac and Windows. Okay, it would work on both. Whereas this would only work on Windows. And that just has to do with how they coded the solver in both operating systems. This is called standard form. And so the Mac solver is an older version which only works in standard form, where you move all the variables to the left-hand side and the right-hand side only has like a constant. That's standard form. Whereas the Windows solver can work on, you know, this non-standard form or the standard form. So I'm going to use standard form. I'm going to put all the variables on the left-hand side, although this is more intuitive, right? This is more intuitive. But because some people use Macs, I'm going to put constraint like this. So when you make your Excel file, whether you're on Mac or Windows, it works. Okay. So if I was just worried about Windows, all I would say is that this cell has to be less than equal to this cell, right? But because I have to worry about Mac, I'm going to do outflow minus inflow. So outflow minus inflow has to be less than equal to 0. Okay. So this outflow minus that inflow, this outflow minus that inflow, this all has to be less than equal to 0. This is flow balance constraints. Outflow minus inflow is less than equal to 0. So that's the constraint I'm putting in here. Okay. And now for this constraint, we're going to have a similar problem, because if I say this outbound has to be less than equal to this capacity, well, this capacity depends on a decision variable. So this can't go on the right-hand side. So instead of saying outflow is less than equal to capacity, I'm going to have to say outflow minus capacity is less than equal to 0. So here again, we're going to have balance or just a capacity, CW capacity constraint. Okay, outflow minus capacity is less than equal to 0. So all I'll do is this, outflow, which is my left-hand side, minus this capacity, and that has to be less than equal to 0. I can drag it down, okay, and this has to be less than equal to 0. Now I'm going to color code my constraints so I know what to enter in Solver. So I did my flow balance constraints for central warehouse, and then I did capacity constraints for CW to turn off based on binary vars. Okay, this is sometimes also called linking constraints because they link these binary variables to this capacity to turn the central warehouse on or off depending on whether we have it on. So if I turn this on, notice this turns on. Okay, so called linking constraints. So these are my constraints. So let's color code them. Okay, so demand satisfied order. That's this constraint right here. So I'm going to color them light blue, not the font, sorry, the fill. And then this is the other side of it. That's just a constant. We'll make also light blue. Yeah. And you can make this light blue too. So that's my demand satisfied constraint. Then capacity constraints of plants are right here. So total going out has to be less than equal to capacity. Okay. Then flow balance constraints are right here. Okay. Let me color them green. These two. Just to show that these, actually let's keep the same color. Blue for constraints just to be consistent. Okay, and then that's my flow balance, and my linking constraints to manage capacity of the central warehouses, turn it off if they're not open, are right here. So all these blues are going to be the constraints in Solver. This is my optimization, my total cost I have to optimize for. So let's set this up in Solver. Okay, this is my model. So if you go to data and you don't see Solver at the right, in Mac you're going to go to tools, add-ins, and you'll see a Solver add-in. In the menu at the top on your Mac, you'll have a tools button, and then go to add-ins, and you'll see a Solver add-in. And in Windows, you see it here. If this button is not there and this does not show up, then you have to go to File, Options, okay, Add-ins, go to Manage Excel Add-ins, hit Go, and turn on Solver, and you might have to turn on Analysis Toolpack. Turn on these two, hit OK, and then after it'll do some processing, and then this would show up here. Okay, so let's open Solver. So this is a minimization problem because you're minimizing cost. You don't have profit to maximize. So make sure you choose minimization. Then the total cost is right here. Minimize this cell. Okay, by changing cells. So changing variable cells are your decision variables. They're all the orange cells. You're going to select all of these. Okay, put a comma and then select all of these. Okay. Okay, so we've selected our decision variables. We've selected our B35, our objective, which you want to minimize. Now you have to add in the constraints. And you also want to make sure to click Make Unconstrained Variables Non-Negative, because otherwise it would allow you to ship negative quantity to reduce your cost, which is, mathematically might be okay, but not okay in real life. You can't ship negative quantities and get money from your transportation companies instead of paying them, right? And so you have to click this to make sure all these orange cells are restricted so that they cannot be negative. They can be 0, they can be 1, 2, but they cannot be negative, right? So you want to click that. And you want to go to Simplex LP. We are doing linear modeling here, so simplex LP is fine. You don't need nonlinear, you don't need evolutionary, so it's just simplex LP. Now let's add the constraints. So to add the constraints, you click the add button. So first one is demand satisfied. So when you, the left hand side is right here. All of these values have to be less than equal to all of these values. Oh no, bigger than equal to all of these values. So bigger than equal to all of these values, add. Okay, then you want to add the capacity constraint. So these values for the plants have to be less than equal to plant capacity. See, color coding helps me. I just go through all the blue areas, right? Add. Then my flow balance constraints, all of these cells have to be less than equal to 0. I can just enter 0, or I can select these cells with zeros. Either way, it's going to work. And then all of these values have to be less than equal to 0 as well. That's my linking constraints. Okay, and now we need one more constraint, because remember we said the central variables open or not is a binary variable, and so you have to specify that as a constraint. You have to go to add, and you have to select all of these cells and choose bin for binary and hit OK, and so that'll make them binary. And if I did everything correct, which I don't know because I'm doing it, you know, kind of with you on the video live, not live, but while recording the video. So let's hit solve and see if we missed anything or if we got everything done. So solver found in solution, all constraints satisfied, keep solver solution, okay. Okay, so here's our solution. We are opening central variables number 2. We are using most of plant 1, 1335, and then some of plant 2. Notice we have not hit capacity on plant 1, but we're still moving to plant 2 because plant 2 is closer to certain, maybe it's closer to certain regional warehouses, and it saves you in transportation expense. Oh no, we don't ship from the plant directly to regional warehouses. The plant 2 is shipping only to central warehouse 2. Okay. Okay. You know, I was expecting actually we would use up all of 1500, but somehow it's optimal to use up 1335 here and 500 here. Even though the variable cost is higher here. You can see the variable cost is higher, but also this saves on transportation costs. So this difference right here is exactly about $15, okay? And then we do save some money here. So it actually is cheaper to use plant 2, not plant 1, because even though the variable cost is cheaper here, when you ship to central warehouse number 2, it's cheaper to use plant 2 because you save so much on the transportation expense. So we actually use plant 2 first, max out plant 2, and then any leftover demand is or requirement is sent to plant 1. And because we're maxing out plant 2, we don't end up maxing out plant 1 because this is so much more expensive to ship. So you can see how even though plant 2 is more expensive, and intuitively you think, oh, let's go with a cheaper plant, the transportation cost more than makes up for the expensive plant, and so it's still cheaper to use this expensive plant because we save money on transportation. And then from central warehouse 2, these are the shipments you make to meet the demand. Nope, I don't want to change anything here. No, I don't want to replace it. Okay. And then my total cost is $349,490. And you can see that all the constraints are being met. Now, if you see these weird numbers like 2.27 e to the minus 13, that is, that means that this is basically 0 because e to the minus 13 means it's 2.27 times 10 raised to power minus 13, or it's 2.27 divided by 10 raised to power 13, which is such a huge number that this is basically 0. And this happens when computers do mathematics, especially floating point mathematics, because computers have limitations on the accuracy of the numbers they can represent. Sometimes you get these artifacts, these tiny numbers instead of 0. So it's fine, it's just 0. Okay. So that is our solution. So, you know, we need to go back, open Solver, and to take a screenshot of that. Okay, so I'm opening the sniping tool. Take this screenshot. And this will put in the Word document for our solver setup. And the second screenshot will be of this model that we will put in the Word document. Okay, so the second screenshot, what I'll do actually is I'll zoom out to capture the entire model in like one screenshot. And then I can take this and put it in a Word document to upload for the assignment for this lab. So you'll have a solver setup and the screenshot, and this screenshot should be showing the final solution, should be showing this answer of 349 for 90, the minimum total cost. Okay, and that is it for, oh no, we have another question. So that's the first question answered, right? That we should open the central warehouse location 2 is the best location. We should open this warehouse with the variable cost of 10, 90,000 fixed costs. And this is how we will run our logistics network to have minimum cost. Next up, we have another question to answer, which is about the service level. Can we fulfill 70% of the demand on same-day delivery? So if you go back to the case, we have answered the first question. We should open Central Warehouse 2 and the associated cost, right? So you can type that answer into your lab document that you're going to submit, that we should open Central Warehouse 2, and the total cost that solver found was, 349,000, whatever, 400 something, right? You can type that in with your screenshots, right? Now let's answer the second question. If you want 70% of the demand to be fulfilled with same-day delivery, how many, because one central warehouse is not going to achieve that, so you want to put more than one. How many central warehouses are required? What is the total cost? So for that, we're going to need the same-day delivery table. So we'll copy it to our model. Okay. We can copy it down here. Okay. Now notice that we did not put a constraint that only one central warehouse could be open. We can sum how many warehouses we open, okay, and we could say that it has to be less than equal to 1 to say that we should only open one central warehouse for the first question that we're answering, right? You could add this constraint. But because opening more central warehouses just adds to your cost as a huge fixed cost, Solver is not going to open a second central warehouse unless absolutely necessary. So you can just run it without the constraints initially to see if 2 central warehouses are best for your situation. But if you're dead set, management only wants to open one, then you can put this in as a constraint. What you'll do is you'll go to Solver, and you'll say that add a constraint that this sum of the binary variables has to be less than or equal to 1. I'm going to just cancel out, and then you could do that if you are required to do that by the question. Okay, so we want to figure out how many of our deliveries are same day, how much of our demand is being shipped same day. So this is our total quantities being shipped. So we can multiply these numbers by these numbers. The ones here will pick out the quantities which are shipped on same day, and we can total that. So we can do same day quantity is a sum product of all the shipments going on. Okay, let me actually move it to the left so that things are lined up. So my RW1 column is lined up, right? So I'm going to do sum product, all the quantities being shipped by this 0, 1 matrix. This is going to zero out the quantities which are not being shipped same day, and it's going to keep the quantities which are being shipped same day. So of the total demand of 1835, 740 of that is being met same day. So what percentage same day is going to be this number divided by this. And we want at least 70%. So this number has to be bigger than or equal to 0.7. We want 70% demand shipments to be same day. 70% of demand met to be from same day shipments, right? So we add this constraint to solver. This cell has to be bigger than equal to this cell of 0.7. Solve again. Okay. So now we end up opening 3 central warehouses. Okay. You can see we open 2, 3, and 4. We're shipping from central warehouse 3, from 2, from 4. And you can notice that we're not using up the warehouses up to their we can decide the capacity, but we're using a small amount of each warehouse. Why? Because we have to do lots of same-day deliveries. You have to be close to the regional warehouses, and this is the traditional logistics trade-off. But a higher level of logistics service, often you need more facilities closer to the customer, and that increases your total cost. Your total cost went up to $490.97. So we need 3 central warehouses, the 2, 3, and 4 ones, and our new total cost is this. And for question number 2, again, you can put in these type in this answer, that which central warehouses you need, what your total cost, put in this screenshot, and then we will be done with this case. You can take this screenshot. Okay. So this is what I need. Okay. So this will put in the document to show the customer service level constraint of 70% same day deliveries. So you can see that in a Word document, you'll put in the first screenshot, you'll put in the answer to the first question and the screenshot supporting it, your total cost, which central warehouse to open. Then you'll put in the answer to your second question. For 70% demand to be fulfilled with same day delivery, we open these 3 central warehouses, and the total cost goes up to this, right? So that's what will go in your Word document for this lab for the answer to this case about case 1 about Papper, the paper manufacturer. Okay, on to the second case, snow removal logistics in Montreal. So here we have, in Montreal, it snows a lot. And when the snow shovels go through the roads and the sidewalks, they just pile up snow along the sides of the sidewalk and the road, and that mountain of snow gets so big that it blocks the road, blocks the sidewalk eventually. So they have to collect the snow, load it up into trucks, and go dispose of it somewhere. Now this is snow mixed with whatever salts and stuff they put on the road. And so this is not just clean, pure snow that they can just dump into a river. They still can, but there's limits and regulations around how much of this salty snow or snow with debris they can dump into rivers and at other sites. So in Montreal, the city wants to do some planning. They have divided the city into 10 sectors. So there's 10 sectors of the city, and they need to figure out how to transport snow from these sectors into disposal sites. And they have 5 disposal sites, each with a capacity in thousands of meter cube given here, 350, 250, 500, so forth. And this capacity depends on whether you're dumping in a large lake that's high capacity, whether you're dumping in a small stream that's low capacity, because you can't inundate natural water sources or fields or open areas with lots of debris and salt-filled compacted snow, right? And so these are our sites we're going to dispose of the snow. And then the sectors are the Montreal city split up into sectors. And then these are the distances. So if you're in sector 1, okay, the closest site to you of the 5 sites is site 2, because it's 1.4 kilometers away, because Canada works on kilometers, not miles. And this is actually a real study that was done in Canada. So there was a research paper published on this. Some university faculty did this modeling for the city to tell them how to cost efficiently, dispose of the snow, right? And so this is this example or this case is based off that real analysis. And the real analysis, they may have had more than 10 sectors, more than 5 sites, but to keep it manageable, we have modeled the same problem, and we're essentially solving the problem with the same complexity, but not exactly the exact same data. Okay, so we know how much snow on average falls on each sector, right? So there's a lot of snowfall in Montreal. So the city estimates that on average, each meter of the street results in 4 cubic meters of snow. So on each meter of a road, because it's also very wide, right? A road could be pretty wide, but each meter along the length dimension and then along the width, that area is going to have 4 cubic meter of snow fall on it throughout this season for the whole year. Okay, so this is like our supply in a way, because when you're picking up stuff, the snow is your supply. You're going to pick up, this is your supply, and you have to pick up all of it, right? You have to use up all of the snow, and you have to move it to these sites, and the sites have a capacity, so they can't receive more than the capacity, but they can receive up to the capacity. So these tables and this transportation rate has already been, these tables have been provided in the Excel file, so the data Excel file. So let's go to Excel and set up this model. And I might go a little bit faster this time because you've already seen how to set up these optimization models in Excel on the Paper case. And also the logistics class has a prerequisite, right? The prerequisite is where you learn optimization modeling and Solver in Excel. So you should all know how to do this already. If you don't know, you should let me know that you took your prerequisite course at XYZ University or with XYZ faculty, and you were not taught how to do solver optimization models in Excel. And then I can fix that problem. I can make sure that course teaches this in future, because this is a required skill you need to have when you get to the advanced supply chain courses. This is should have been covered in the prereq course, right? So you should not be learning this from scratch. You should already know this, but you should review and applying it to more realistic problems. You may have done smaller problems with less variables, but we're doing the same algorithm, the same optimization tools at a little bit bigger problem. So the type of problem or the act of optimizing using Solver should not be new to you. You should be familiar with optimization using Solver. So we have two questions again. We want to find the minimum cost plan, okay, which sectors will be dumped into which sites, okay, and then we have to say if we could increase the capacity of a single disposable site by 100,000 cubic meters, which is it worth it to do that? Like, does it reduce our total cost, right? Because it's going to cost us something to increase the capacity, right? And how much will you be willing to pay for this extra disposable capacity is going to be a reduction in cost. If our cost was, let's say, $1 million and it goes down to $800,000, the $200,000 of cost savings we get from this additional capacity, well, we can pay up to that amount to set up this additional capacity, right? You don't want to set up additional capacity for $500,000 and only save like $200,000. Then you're losing money, not you're not saving any money. So let's set this up in Excel. Okay, I'm just gonna put in transportation rate here as well. Okay. So it costs us $0.1 or 10 cents to take 1 meter cube 1 kilometer, right? That's our transportation rate. So I'm going to make a new worksheet called model, and we're going to model that. So let's think about our decision variables, right? So each sector can logically send stuff to each site. So whether a sector is going to be sending something to a site, that's going to be a decision variable, like whether I send sector 1 to site 1 or site 2 or site 3 or site 4 or site 5, right? That's going to be a decision that I have to make. So that's going to be a decision variable. So our decision variables are going to be, how much snow gets moved from each sector to each site. And we don't have any fixed costs. Actually, a simpler problem than the last one. We don't have to worry about fixed cost of running these sites, just dumping grounds or dumping areas, right? So let's set up our model. I always copy this tables like this, because I'm going to need decision variables right here, so I can just copy this and delete the central part to make my decision variables. And I need to keep this table somewhere here on the side, because I'm going to need the cost, or I can do it like this. Okay, and then this, actually let me put it to the side. Oh, this is down here. Let's move it up here, put it also here. Okay, so these are going to be my decision variables. Model has to figure out from each sector how much snow to ship to which site. And then I have my transportation rate. So I'm going to copy that. So I might need that to calculate my transportation cost. And then the total snow lifted from each sector is going to be the sum of each row. So if I sum up these values, which is how much snow goes from sector 1 to each site, that's the total snow lifted. That has to equal the snowfall, right? Because I have to pick up all the snow. So here's my snowfall, my snow removal requirements, okay? And then however much snow my trucks lift, right? That has to match the snowfall, has to be equal. We could put greater than equal to, but we know it's never going to be greater because you can't pick up more snow than what falls, right? And we can't do less than equal to because you have to pick up all the snow. So it has to be equal to the snow that falls. This is the snowfall, that's snow lifted. And then the snow that goes to a site, so that's snow dumped at a site, snow dumped, or snow at site. So sent to site is going to be the sum of the columns. That's the snow that goes to site 1, right? And that has to be less than equal to the capacity of the site. So we have the site capacities, which we'll copy here. This is capacity, right? Okay. And then I need my total cost. Okay, that's going to be some product of how much snow I pick up times the distance, because snow times distance times the transportation rate is going to be my shipping cost. So if I ship 1 unit here, so that travel distance of 3.4 kilometers times 0.1 gives me a cost of 0.34, because 3.4 times 1 times 0.1 is 0.34. Okay, let's make this 0. What if I ship 1 here and 1 here? Then this 1 cubic meter travels 1.4 kilometers, giving me a total cost times 0.1 rate gives me a cost of 0.14, and this cubic meter travels 4.7 kilometers times 0.1 gives me a 0.49. 0.14 plus 0.49 is $0.63. So my cost formula seems to be working well, and Solver will decide these values. Let's color our constraints blue, the color of snow, so that when we are putting them into Solver, we remember to get all the constraints. So orange decision variables, constraints. This is going to be my objective value, and minimize this. So you go to data, Solver, set objective. This is my objective. Please minimize this. Don't maximize it. It's a cost. By working on these decision variables, and then I'm going to pick up all the snow, so all that has to be equal to this. And I don't have to do any adjustment for MAC, because the right hand side of my constraints are just numbers. They don't depend on decision variables. They're not formulas, right? So I don't have to do any MAC adjustment with the LHS, right left hand side minus right hand side less than or equal to 0. I don't have to do that. And the snow dumped at a site has to be less than the capacity of that site. Those are my two constraints. Make sure you do simplex LP. Make sure you make unconstrained variables non-negative. Otherwise, Solver will start shipping negative quantities to earn money, because Solver thinks that shipping negative quantities will give you this money, which is your transportation rate, right? But that's not true. So I'm going to avoid that. And if I set everything up, let's hit solve. and it says solve for a solution, all constraints were satisfied, and here is our solution. It's going to cost us $478. Okay, this is going to be in thousands because this is all thousands, right? So this actually is thousands of cubic meters. So 1 cubic meter costs this much. So you actually have to multiply this by 1,000. This is your cost in dollars. Okay. How do I know that? If you look at the data, thousands of meter cube, everything is in thousands, right? It's thousands of snowfall in meter cube and thousands in the capacity. This is per meter cube. This is not per thousand. So you have to multiply your total cost by 1,000 because otherwise you will getting the cost. You were not factoring in the right. Your cost was not in dollars. Okay, so our cost is $478,490. This is our plan for sector 1. We're going to ship everything to site 2. So all snowfall shipped to site 2. Sector 2, we're going to split up some to site 1, some to site 2. Why? Because site 2 is now full and you can't send any more. Even though site 2 is closer than site 1 for sector 2, site 2 gets full at 250 and you need to send the rest to site 1, right? So capacity comes in. And so now we have a nice shipment plan or snow removal plan, and we give this to the city and say, have trucks send everything from sector 1 to site 2, have trucks send in, about 2/3 of the initial snowfall to site 2, and when site 2 is full, switch to site 1, and then sector 3 send it to site 3, and then some will be left because the sector 4 and 5 gets there, then send the remaining to site 1, and so on. You can make a nice plan and give it to them based on this analysis. So again, you can take a screenshot of this model. Okay, this much is enough. And then you're going to write your answer that the total cost is going to be $478. Now we still have one more question to answer about capacity expansion. Okay, so in your Word document, you'll type in your answer for the total cost. You'll show your model, and you will also show your solver screenshot. Let's take the solver screenshot. Okay, and we'll put this in our Word document. So your Word document will have these two screenshots: solver, your model, and the total cost. Okay. Okay, now let's do the second question, which is if we add 100,000 cubic meter cube of capacity at a site. Okay, so we will put in a binary variable. Okay, that'll be additional capacity, and 100,000 cubic meter cube is just going to be 100,000. So it'll be 0, 0, 0, 0, 0, or 1, right? So it'll be 1 for whichever site it makes sense to add 100,000 cubic meter. Okay? And then the capacity at whichever site you add this to will go up by 100,000 or 100 in this case, because this is in thousands of cubic meter. So we'll do 350 plus this variable times 100 will be my new capacity. So if this becomes 1, my capacity goes up to 450. If this is 0, I don't do expansion, it stays 350. So I have to do this to all of them. Okay, so instead of doing it here, let me put it back to 350. I'm going to do it here. Okay, new capacity, okay, is going to be this times this. Oops, sorry, no. It's going to be this plus this times the additional capacity that I can put in there. Put in 100 here. This is my capacity, new or expansion capacity. Okay. Yeah. So if I make this 1, this becomes 450. If I make it 0, The new capacity is the old capacity. Okay, and now here you want to make sure that this cell K16 is 100, you put $sign so it doesn't move, you lock it in. So when I drag the formula, everything still works, and then I can turn on any one of them. Okay, see, and I want to make sure I don't expand all of them, so I only want to expand one of them. So I'm going to sum these, okay, and make sure that this equals 1. Okay, so I only expand one of them, only one of these could be 1, and then I get the new capacity here, which I'm going to update the capacity constraint to make sure I use the new capacity. Okay, so this will no longer be part of the constraint. Okay, now here's the problem. On this number, snow at site, being less than or equal to this number, now this number has a decision variable right here in the right hand side. So I have to do this will not work on Mac. So I have to do the LHS minus right hand side and make it less than or equal to 0. Okay, let me add a row. So here I'm going to put this has to be less than or equal to this. So I'm going to do this minus this has to be less than or equal to 0. Okay. Okay. And my new capacity, all of this is not a constraint. Although my new capacity is an important variable, so I'm going to color it purple bold, but this is my constraint. Okay. So remember I just did this, just like outflow is less than or equal to inflow, but Mac had the problem, so you do outflow minus inflow is less than or equal to 0. I did the exact same thing. I had snow dumped at a site less than or equal to capacity. Now when capacity was a number, it was fine, it would work on Mac, but when capacity became plus the binary variable times 100 additional capacity, now this has a variable in it, and now it can't be on the right hand side for Macs. So now I have to do snow dumped minus capacity, including the binary variables times additional capacity, has to be less than or equal to 0. I have to put it in like this. Okay, so this is my new constraint for the new capacity. Now we go to solver. Okay, look at your old capacity constraint using cells like B18 to F18. This one, you want to change that, and instead of this B18 cells, we're going to use these cells, and then they have to be less than or equal to, you can type in 0, or you can just select these zeros. Okay, and then we have to add a constraint that we want to expand one of the sites. Okay, and remember the old cost was 478490. Okay, so there was some mistake. Oh, I did not add these as addition variables. That's why it's messing up, because it cannot change these cells, because I never told it you can change these cells. So I have to go here, put a comma, and you can also change these cells, solver. And I have to add a constraint that these cells are binary. And now, nicely done. We want to expand site 1, and our new cost is 45510. So our old cost, okay, our old cost we put into the Word document was 478,490. Okay, 478,490. Okay, so the cost savings by this expansion are going to be this minus this. So we'll be willing to pay $23,390 or less to do this capacity expansion, because that's our cost savings. Obviously, if you expect more snowfall to fall in the coming years or less to fall, this could change. This is based on your forecast of the snowfall that you expect on average to happen. But currently with this forecast, if we add 100,000 cubic meter of capacity, the best place to add is site 1, and then you save $20,390, right? So again, for this question, you'll take a screenshot of this model, okay? And then you'll type up your answer in the Word document. Okay, so here I've put in the screenshot in the Word document, and I've typed up my answer. That site 1 should be expanded as it saves $23,390. Max cost of capacity expansion should be less than or equal to the savings of $23,390. Because if you spend more than that, then you're not really saving any money from a financial perspective, because you're saving on the cost of removing the snow, but $23,390, and you're spending more than that to expand the capacity. So it doesn't make business sense. Okay, so that's would be the answer to the second question. Okay, so this is how we do solve logistics problems in Excel. Both cases we did are very realistic cases. Opening a central warehouse to feed small regional warehouses or retail stores. Which site to pick? That's network optimization. A small little removal plan. Similar models can be built for garbage collection planning and so forth. So this is always a very powerful tool, and I hope with this lab you gain more experience and more comfort in modeling and solving these types of problems. So please remember to upload your Word document with all the screenshots of the solver setup, of your Excel worksheet setup, and your final answer on what the costs you achieved on Canvas on the submission link. That's it for this lab.